All right, so why do we care about how many significant figures are in a measurement? Well, we saw the relationship between what is measured on an instrument and how that translates into significant figures. Which brings me to the accuracy and precision thing. Could someone define accuracy for me, please? This is something you're supposed to have had in a previous class, but it may or may not have either happened and or been remembered by you. What is accuracy as it refers to a measurement? Give me a second. Last name is Day. First name, I have no idea. Peyton. Go ahead, Peyton.
How close something is to being exact.
What does exact mean? And anybody can help her out here. You were headed in the right direction until you said that word. I don't know what that means. Anyone want to help her out? Well, then let me try it a different route. What does the word precise mean, or precision? Go ahead. Or are they the same word? Error. You're having trouble, correct? What do you got? Wait. Eye or ear? Okay, Akira. There we go. That is one definition of precision. There's actually two. That's one. What does accuracy mean? And then we threw that word exact in there. What do you mean by exact? Oh, now the correct measurement, the one that is known to be true. That's better. Okay, so here we go. Okay, so here you guys get, because you're good students, I'm going to give you these definitions, and you're going to write down exactly what I say. I say something different every year. I'll say something different each period that I talk about this in. So you will never be given a vocabulary test. This is not English class. Try to absorb the information and make it make sense to you before you start writing anything down, okay? Because then I have to repeat it 8 times. What did you say, Miss Lehman? What was that 15th word, Miss Lehman? Okay. Accuracy refers to, and Akira said it correctly, how close a measurement is to an accepted value or one that's known to be true. So now you're going to have to compare it to something. Whereas precision, and again there's two definitions, we're going to differentiate between this and accuracy. We'll go back to the one Akira said earlier. Precision refers to the amount of information that a measurement has available to it, or in other words, how many decimal places. So, an example there would be clearly which measurement is more precise. The 27.78, because there's more information available. Does that make any sense where I'm going with that? Which one is accurate? Go ahead, Josh. Oh, you actually did the right whatever gesture. Gesture went like this. Josh went like this. Which one's accurate? We have no idea. Why don't we have any idea? We don't have anything to compare it to. We don't know what the accepted value is. Now, those accepted values are going to come from a couple of different places. Usually, they're going to be things that we look up somewhere in a big book of constants. It doesn't even, I don't know, a couple thousand. It doesn't really have it by pages. It has it more by sections. Yeah, there's no pages. Okay? So accepted values are either going to be provided by me or you're going to look them up somewhere where someone has done repeated experiments in order to come up with an average accepted value. See where I'm going with that? So yeah, we can say which one's more precise, but we have no idea which one's accurate because we don't know what to compare it to. Now, let's go back to Akira's original idea on precision because that's the second way we will look at precision in this classroom. Okay? And there's going to be a handful of labs, not many this year, because for this class, we're just trying to learn how to do things and learn some techniques and get some general ideas of how things work out. When you get to the AP class, we're going to do more labs where we're going to do multiple trials so that we can compare our results amongst trials. But let's say, and there's going to be a lab we're going to do really soon here, you're going to be determining a constant for a substance, and you're going to do 3 different trials. Okay? Let's imagine that your results for these 3 different trials are 3.89 grams per milliliter, 3.87 grams per milliliter, and 3.90 grams per milliliter. That was the result of your 3 trials. What can you say about the how close those results are to each other? Are they pretty close? If you got that, that would be phenomenal. That would be very, very good. Okay? The furthest they're away from each other is 3/100ths of a value. Would you agree? That's pretty darn good. Okay? That means these 3 measurements or these 3 results displayed high precision. You have confidence in your technique in that you were getting the same result every time, or a very close result every time. High degree of precision there, okay? Could someone, what's the average of those values real quick? Okay, what's a really good estimate of the average? Right around 3.8. Okay, go ahead and do it. You're trying. Final answer? Right. Or it's probably 3. What is it? Okay, 6. Okay, so 3.8667 or 88. Okay, so there we go. Okay, is that average accurate? We don't know because we don't know what the accepted value is. Okay, so let's say I told you the accepted value is 3.879. Is that accurate? Oh my gosh, it's incredibly accurate. Okay, you will never, probably ever do a lab in this class or anywhere in which you're going to get that accurate. Okay? So, however, what if I'm guessing here. Give me a second here. Could you do that real quick? You guys are going to need your calculators out anyway, so you might as well all get them out. Dang it. That's pretty good. That's a pretty good guess on mine. 31916, so we'll just go 2 grams per milliliter, okay? Now, is this value relative to this pretty accurate? That's still pretty accurate. Did you guys ever do a calculation called a percent error calculation at some point in your lives? Does that sound familiar at all? Okay, it's a really quick and easy calculation. I'll teach it to you later. I'll show it to you later. But once again, that 3.92 is actually pretty good. Okay, we're talking less than 5% error here. In a high school laboratory setting with you guys doing things for the first time ever, that's pretty darn good, okay? With that being said, in which average do you have more confidence in? These over here or these? Let's do this. A and B. B, why? It's more precise. We have greater... This was possibly a lucky guess by someone, because we were ranging anywhere from 4.2 to 3.6. That's a pretty good gap. They got lucky. They really didn't know what they were doing. Okay? Whereas this, we're getting very consistent results. So both things matter. Okay? You want high precision if you're doing multiple measurements, and also you want clearly some good accuracy. Are we a little bit better on the difference between the two ideas? Excellent. Moving on. Okay. Well, I'm going to read something to you. No, I'm not. Let's just move on. Let's just get this done. When we're doing calculations with measurements, we have to keep track of the precision of our values. And where I'm going with this is, what if I were going to measure the perimeter of the room? What measurements would I have to take? The length of a wall. Just one wall? All of the walls, and then do what? Add all of them up. All right. So let's say I measured the length of that wall and this wall with this instrument. To what decimal place should my... Now, what is that thing? It's a meter stick, which measures a meter. So your answer has to be stated in terms of a meter. Okay? So to what precision level? How many decimal places? I gave them the hard one. Actually, it's the easy one. Go ahead. Of a meter? What do the little lines represent?
Just the decimal point, and then like the ones are like the ones.
Okay, this is a meter.
Yeah.
We'll let them try. What you got?
3. What is it?
We're measuring in meters. The smallest lines represent the thousandth place. Therefore, we can estimate in between those small lines and get the 10,000th place. So let's say I measured the length of this wall was 18.7892 meters. I measured that wall, and it was 11.4286 meters. Excellent. Then I'm going to measure the length of that wall and the length of that wall with this instrument. What is this? No, what is this? There are no markings. Yes, you're seeing all the markings you're supposed to see. It's a stick. Meter stick. So how long is this thing? A meter. To what place should this instrument be read in terms of a meter? The ones place? So 0, 1. I can't estimate? Where am I? 0, 1. Did you just say a fraction? No. You didn't say a fraction. Oh. What do you got? 0, 1. 0.8. Okay, not bad. Not bad. It was 0.7, but okay. But still, okay. But there's no numbers. How did you get that? Estimated. Okay. So the precision level of this instrument that are no intervals other than 0 and 1 would be to what part of a meter? See, remember I was making fun of freshmen earlier? Yeah. Guess what we're going to have to do? I'm going to have to teach you guys how to measure. I mean, I did all this stuff, right? And okay, yeah, I get it, okay. But when you get a real instrument in your hands, you guys are going to screw it up. Happens every time. Anyway, we're demonstrating that right now. 0, 1. To what decimal place can this instrument be read? The 10th place. There's no divisions. So we know the ones place. What are we going to estimate to? The 10th place. So I measure that wall and that wall. And I get 18.5 meters and 11.2 meters. Okay, so now how do I get the perimeter? Add all those up. So somebody do that real quick. Okay, I got it. 8, 17, 11, 12, plus 7, 19, 16, 17, 18, 19, 1, 2, 3, 5. There we go. Whatever. I just did it real quick. Oh, like that you mean? Yeah. You're having a tough day, aren't you? Yeah. Anyway, moving on. How confident am I that the perimeter of the room can be stated to the 10,000th place? Why aren't I very confident? One of the instruments was not precise enough. So how could I state my result with any degree of confidence out to here? Does that make any sense? I can't really state the perimeter out to that precision when one of my instruments really only was valid to there. Are you seeing where I'm going with that? So it matters. The precision of your instruments matters. The quality of your instruments matter. Okay? So I just introduced you to one rule for doing significant figures, determining significant figures in calculations. There's actually like 4 different rules. Currently in this class, up until about almost April, we're only going to need 2 rules. There's a whole set of rules for logarithms too, but we're not going to do anything logarithms until about April or so. So here we go. We have an addition and subtraction rule. Okay? So anytime you're adding or subtracting numbers, and I just demonstrated that actual rule, by the way, but now you saw an example of it. With addition and subtraction, the result is stated to the same level of precision. The result is stated to the same level of precision as the least precise measurement. With addition and subtraction, the result is stated to the same level of precision as the least precise measurement. Now, looking at the example I did with the perimeter, which were the least precise measurements? The ones that were stated to the tenths place. I can't remember the numbers that I had written down. Dang, did anybody happen to write any of those down?
It's like 18.789.
Okay, hold on. 18.7892. And 11.6? 2. Okay. And we got, when we added it all up, what was that value? 59,9178. Okay. So we do all this work on our calculator, right? We look at the set of measurements that were taken to get this result. We see that these two are the least precise measurements. They're only precise to the tenths place, correct? We need to round to the tenths place. So I kind of misstated what I said. Did I say state the result?
Yeah.
Okay. Round the result to the result. The result should be rounded to the same level of precision as the least precise measurement. So, on a test or a quiz, you were finding a perimeter of something. Who knows? Who cares? Okay. These were the data that you were given. This is the result that you got from your calculator, actually using your brain. Weird. Okay. And so to correctly state that result, your correct answer would be 59.9, what was it, meters? There's the correct answer. Easy rule, wouldn't you say? It is. Both rules are really, really easy. That's incredibly easy. The next rule, the one for multiplication and division I'm going to give you, is also very easy. Where you guys start making mistakes is mixing and matching the rules with the operations. You know what I'm saying? So you just have to be really careful. So here we go. Let's try the multiplication and division rule. Let's do an example. Let's say I want to find the area that doesn't matter. 11.2, I think it was. Doesn't matter. Let's find the area of the room. Now, what do I need? The length of one side, the width of another side. Would you agree? Sure. And what are you going to do with those measurements? Multiply them. Could you please multiply those? Someone. I don't care who. Just give them all to me. 43904. Is that all? Yeah. Really? Okay. And what is the unit? Meters squared. Okay. So here is the again, and I'm not going to go into a lot of details with this, but once again, after that addition and subtraction rule, we kind of get the idea that the precision of the instruments that we're actually used to take the measurements influences to what level of precision we can state our answer. Okay? When we're doing multiplication and division, here's the rule. The result should be, and I'm going to say this correctly this time, rounded to, how was Florida? How was Florida? You were somewhere really nice. You had a big smile on your face. You were just like, it wasn't Florida? No? Okay. Anyway, the result should be rounded to the same number of significant figures. Notice this time I said number of significant figures as the measurement with the fewest significant figures. Would you like me to repeat that 3 more times? The result should be rounded to the same number of significant figures as the measurement with the fewest number of significant figures. So looking at this big hunky-dory mess we have up here, we see a measurement that has how many significant figures?
5, 6, 7.
Are you just counting digits?
Yeah.
How many? 6. How many significant figures here? 3. So my answer can only be rounded to 3 significant figures, which in this case is here. Oh, this is a great example. I am going to use this one all day long. As you can clearly see, I make things up all day long, okay? Every year. I don't have, like, notes. Sometimes I get really good ones. I'm going to save this one. Anyway, so I need to round that result to the ones place. How would I write that down as an answer to a quiz or a test question? 210, someone said. Well, there's a number of different options from here. Least favored ones. That or that. Best or most favored one. But either way, we'd have to show our result of 3 significant figures. Everyone hunky-dory? Well, okay, and in that case it would be meters squared. Is that rule easy? It's incredibly easy. Can you see you mixing and matching the rules a little bit, forgetting which rule goes with which set of operations? Right. So just be careful and know your rules. All right, I need to take a picture of that because that was a good one. Anyone want to get in the picture? No? Okay. All right, well, clearly you guys are going to need a little practice with this, but I'm not going to how much time do I have? Okay. Let's do a couple real quick examples. There's really 2 or 3 more ideas that are going to come out from all of this. Oh. Did I get that one in there? I did. Okay. So let me see. We've got an addition, an addition. We should probably get a subtraction in there, shouldn't we, just to balance things out? 165. I can't remember what it is. 165.38 minus. I'm going to rewrite that one because it's pretty sloppy. Can everyone read all of the values? Okay. And again, since we have, well, we have what? A multiplication, we have two additions, we have subtraction, and ooh, what do we have here? We have a couple of different operations, don't we? I'm going to let you guys play with that one on your own and see what you come up with. How is that possible? Mrs. Danhoff must be bored currently. Her and I are in a Words with Friends game, and she just played. What is she doing? Time does this class get out? 45? 05. We have 2 minutes. So how many more young siblings do you have, Miss Gray?
How many younger?
How many? Yeah, because Emily's the oldest. Yes.
Yeah. The only other sibling that you'll have is Brian.
Okay. I mean, because I'm old and I'm going to retire soon.
No, some of them just have their opinions.
Oh, okay. Well, I am old, but I'm not going to retire soon. I didn't start teaching until I was 30, so yeah, I'll be 82. So maybe tomorrow we should measure a little bit, huh? Just for fun. All right, well, we will look at the correct results on this tomorrow. Want me to write them down real quick? Here, I'll tell you what the correct answers are. Don't erase anything that's on your paper so that we can have a little discussion. If you were going to round these to the correct number of significant figures, this one would be 9.3 meters. This one would be 4.0 times 10 to the second centimeters squared. This one would be, where'd it go? I lost it. I lied. No, wait, that's right. Oh, here it is. This one would be 35.3 milliliters. This one would be 0.6 grams per milliliter. And this one would be 60 liters. Those are the correct answers. We'll pick those up tomorrow.